Hi, Math310, Spring 2020, Simon Fraser University. This is part B of the 5.2, 5.3 series solutions near an ordinary point. So just to recap where we're at, we had gone through talking about what the series solution method looks like. We've done an example. This is in part A of the lecture. And we had gotten to this point here where I had defined an ordinary point. So right now we're talking about series solutions in the neighborhood of an ordinary point. Okay, just a couple of theorems coming here to make sure that what we're doing is valid. If we have two solutions, so I'm saying y1 and y2 are two solutions to a second order differential equation of this form right here, and I'm given initial conditions that look like this. So at the point x naught, I have an initial condition on the function y1 and y1's derivative, and I have an initial condition on y2 and the derivative of y2. And if the initial conditions are like this, 1, 0, 0, 1, then I claim that these solutions, y1 and y2, form a fundamental set of solutions. So that's quite straightforward to show, and we will be using the Wronskian like we have many times in the past. So let us consider the Wronskian of y1 and y2 at x equals x naught. What does that look like? Well, that Wronskian of y1 and y2 is the determinant of, and this is, I want to be super clear here. That is going to be evaluated at x naught, and that is going to be the determinant of y1 at x naught, y1 prime at x naught. Let's put that in the right place. Y1 prime at x naught, and then y2 at x naught, and y2 prime at x naught. I have all those values. I've been given them. They're right here. So let me just put those in. That's going to be the determinant of this matrix right here. That's going to be 1, 0, 0, 1. That determinant is 1. So therefore I can see that the Wronskian is not equal to 0. And that immediately tells me that y1 and y2 form a fundamental set. Okay, theorem. Another theorem. Suppose we have an ordinary point, and that means that P and Q are analytic at x naught. Then for any numbers, y naught and y1, there is a power series solution to this initial value problem with those two initial conditions. And the radius of convergence of that power series solution is at least as large as the minimum of the radius of convergence of the power series for P and Q. Because this is getting at the same concept we had before of the interval of validity. Let us take another example. I'm going to say some things about what I'll expect you to be able to do when we're solving these at this point. We're going to have to treat this topic fairly lightly because we don't have a lot of time left in the course, and we're not going to be as fully rigorous as we perhaps otherwise could be. Okay, so now we're going to find the general solution of Airy's equation. Here it is, y double prime minus xy equals 0. So differential equations that have come up in the context of an important physical process typically often are named, and then the function that arises from solving them usually carries the same name, maybe Airy's function or something like that. So we'll see, for example, also the Bessel differential equation, and then Bessel's functions. And so if we see a named equation, that should make you maybe aware that this has been important in some reason in the past, and also maybe to think about looking it up, like, I wonder what this is about. And in this case, the Airy's equation came about in the study of optics. Okay, we can take a look if we were to put this equation into the format that looks like this: P of x, or y double prime plus q of x y prime plus r of x y, and look at what functions we've got. We've got very simple functions. That is, p of x is 1, q of x is 0, and r of x is minus x. Okay, every point is an ordinary point. We don't have to have any worry about the points not being ordinary. Every point an ordinary point. Okay, so the method is going to be exactly as we did before. We are going to assume a power series solution. There it is. Only remaining problem is to figure out what those xn's are for this particular differential equation. We're going to, when we start this thing, we could assume it with some radius of convergence. We're going to see that that's actually going to be infinite, but this would be a classic way to start. Okay, then we're going to take the derivative, and I will get this here, n equals 1 to infinity of n a to the n x to the n minus 1. I will take the second derivative, and I see that I need the second derivative, and that's going to be n equals 2 to infinity n minus 1 a to the n x to the n. Okay. Hang on, I'm thinking here. I think something has gone wrong here. This should be n minus 2. I'm taking the derivative here, so I'm bringing down that exponent n minus 1, and I'm reducing the exponent by 1. Then what I'm going to do, which is why we did that little typo thing there, is I'm going to adjust the indexing so that it starts at 0. So now I'm saying that this power series here that I've got for the second derivative is exactly the same as this power series here. I'm replacing n by n plus 2. I'm replacing n with n plus 2, and then this becomes x to the n. Why did I do that? Because I am headed towards adding this power series, because I see that it's going to be here in y, to this power series. And this one is going to be in here. So I'm anticipating that I'm going to need to have the indexing starting at the same place, and potentially having these things here like this. I still may need to make further adjustments. Let's just see what happens. It doesn't have to be done either exactly the order that I'm doing this, but the key feature is you have to be able to take the solution, differentiate it as many times as necessary, replace the function into and its derivatives into the differential equation, adjust the indices and the powers on x properly, and then get a recurrence relation on the values of an. Okay, so now I've done my assumption, I've done my couple of derivatives. Now I'm going to substitute into the differential equation. Okay, that is this thing here, obviously, y double prime minus xy equals 0. Okay, so I take the expression I have for y double prime, and that is this here. I subtract x times the power series I have for y. And I write that out like this. What did I do here? Okay, I moved this x right here inside here, and that's why that became here n plus 1. Okay, now I have that same issue where I see that I have got different exponents here, so I'm going to take this one here, replace n by n minus 1, and I'll write that out. And I will also at that point realize that this thing is going to start at 1, so I am going to have to take out the first term from this one. So because they need to both start with the same index. Okay, so that will look like this. I'm taking out the first one from here, so that'll be 2 times 1 times a2. That is the n equals 0 term. And then here's the rest of them. N equals 1 to infinity, n plus 2, n plus 1, a, n plus 2, x to the n. And then I will have the modified version of this one here, which is n equals 1 to infinity of a to the n minus 1, x to the n, and that has to be equal to 0. And now I'm in the happy situation where I can put these two infinite series together. That's going to be 2a2 plus the sum n equals 1 to infinity. And what do I have? I have the coefficients on xn, n plus 2, n plus 1, a to the n plus 2 minus a n minus 1. That is the coefficient on xn. It's equal to 0. Okay, all the coefficients have to be 0 on the left-hand side. All the coefficients are 0 on the right-hand side. All the coefficients on the polynomial on the left-hand side have to be 0. Immediately that tells me that a2 has to be 0. So immediately I got here, if this is from all coefficients must be 0. I will get here that a2 will be 0, and that also this expression here must equal 0, which means that n plus 2, n plus 1 times a n plus 2 is equal to a n minus 1. That's for n equals 1, 2, 3, etc. Okay, further, okay, so what do I know? I know a2, and then I know here an plus 2 is an minus 1 divided by n plus 2 times n plus 1. I know that. And I am missing, right now, I am missing a0 and a1. Where would those come from? Let us take a look at what y of 0 is. Y of 0 is the sum from n equals 0 to infinity of an x to the n evaluated when x equals 0. And that is simply a0. Similarly, y prime of 0 is the sum from n equals 1 to infinity of n a to the n x to the n minus 1 evaluated when x equals 0. And that looks like this if I write out the terms. a1 plus 2a2 x plus 3a3 x squared plus dot 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 evaluated at x equals 0. And that is a1. So now I have two more important pieces of information here. a0 is y at 0, and a1 is y prime at 0, our initial conditions. Okay. So I have a0, a1, a2, and then I have an expression for finding a3 in terms of a0, a4 in terms of a1, a5 in terms of a2, and I can keep going. So in fact, now my problem is solved. I have a power series solution for my that solves my differential equation, and I have a way for finding as many of the coefficients as I want. Let us be a little bit more compact with our notation. and see what else we can say about this. A0 determines A3, A6, A9. How do I see that? Well, the difference between n plus 2 and n minus 1 is 3. So if I plug in n is equal to 1 into that equation, I will get A3, and then when I plug n equals 1 into here, I'll get 3, and when I plug n minus 1 into there, I'll get 0. Similarly, so there's a difference of 3 between n plus 2 and n minus 1. So A0 determines all of these ones. A1 determines A4, 4 being 3 more than 1, and then similarly A7, A10, etc. And A2, which is equal to 0, determines all of these ones, A5, A8, A11. So it immediately follows that all of these are 0. Okay, now we'll take a closer look at what A3, A6, A9 are. Okay, so those ones, taking a look at this row here, A0, A3, A6, A9, that is using n equals 1, 4, 7, 10 in our recurrence relationship. We can then see that A3 is A0 over 3 times 2. Now I'm simply using this formula right here when n is equal to 1. Then I'll use it when n is equal to 4, and that will give me A6. So I get A6 is equal to A3 over 5 times 6, but I know what A3 is. A3 is A0 over 2 times 3, and then there's 5 times 6. Then I compute A9. A9 is A6 over 8 times 9, and then that is, I know what A6 is. A6 is A0 over 2 times 3 times 5 times 6 times 8 times 9. And I keep going, and again I see a pattern. I write out, based on the pattern I'm seeing, I write out A3n is A0 over 2 times 3, 5 times 6, etc., etc., and I go up to 3n minus 1 times 3n. And in this case here now, I've sort of changed the meaning of n. It's a bit unfortunate, but I'm looking at these specific values here now of n, and when I've done it in this matter, because I've put this 3n here, now I've just got n equals 1, 2, 3, 4 like this, like that. So I hope that's not confusing, but that is now an expression for all of the values of a, the coefficients where it's a multiple of 3. Okay, then I'm going to go again on the next one. So I just did this one here, and now, so that one went there, and now I'm going to take a look at this one here. I'm going to come down here, and I'm going to be using n equals 2, 5, 8, 11, etc. And I end up with the following computations. Maybe pause the video, see if you can calculate them yourself, and then come back and check. But this is I'm now using the recurrence relation just like I did before, and I'm using it with these values of n that I've eliminated here. That's A4 over 6 times 7. And I know what A4 already is. It is A1 over 3 times 4. And I get 6 times 7, etc. And I keep going. A10, that to be A7 over 9 times 10. And then that is A1 over 3 times 4, 6 times 7, 9 times 10. Okay, I keep going, and then I see the pattern in this one, and I recognize that these ones look like this. 3 times 4, 6 times 7, and I would keep going up until I got to 3n plus 1. Again, now this is where n is just greater than or equal to 1. So now I've got that expression there, and I know the next batch are all 0, so I don't need to worry about those ones. And I'm going to put these two boxed expressions for the coefficients of my power series together and write out what the solution to this differential equation, to Airy's equation, it is. So we're calling the differential equation looks like this. There it is. It looks actually remarkably simple. And now I know if I had that differential equation, here is the solution. A naught, and A naught is, what is A naught? Let's scroll back and remind ourselves, what is A naught? A naught is the initial condition on the function at 0, and A1 is the initial condition on the derivative at 0. So I here have y of 0, and then I have these terms here, x cubed over 2 times 3 plus x to the 6 over 2 times 3 times 5 times 6 plus dot 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 plus x to the nth term looking like this, 3 over n 2 times 3 dot 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 3n minus 1, 3n, and then plus dot dot dot. These are infinite series, and then I have to write the other ones here because they're not exactly the same. I can't put them together in one piece. And then I have here x to the 7, and I get 3 times 4 times 6 times 7, and then I keep going. I put the general term looking like this, 3n plus 1 plus dot dot dot. Okay, there it is. That is, folks, the solution to the differential equation. It maybe doesn't look as nice. It's not as compact per se as what we've been seeing in the past. However, we now have an infinite polynomial, if you will, a power series, and we could simply choose to take 100 terms or 50 terms or 5 terms or however many that we like, and we can compute for any value of x. We can compute what the value of the function is. So you give me an x, I can compute what is y of x. So it is a function just like any other one. However, when we compute the value, we're going to have to accept a certain amount of error because we're going to have to truncate after some finite number of terms. I'm going to say, simply state, this converges. This function, this y of x converges for all x. And why am I declaring that? I'm looking in I see the almost factorial in the denominator. So I'll make a note of that. The almost factorial. That's always a good sign for for convergence. But that, of course, is not rigorous at all. If you wanted to verify for what values of x this function converged, you could check using the ratio test. I'm not going to require you to do this. Okay, we could also use the theorem that says we know the radius of convergence of p of x and q of x, and this thing will have the at a minimum the minimum of those two. And all of our points being ordinary, we have an infinite radius of convergence. Okay, so you can do everything that you can do with this function that you can do with other functions, and that is you can plot it by terminating and yielding a polynomial approximation that allows you to plot it and calculate values for it, take its derivative, integrate it. You can do all of these things. So it's just it's like a regular function, but it's not represented perhaps in the way that we're totally used to. And just to sort of make this point maybe a little bit more strenuously, consider a function that you have been using for many years. Cosine of x, and then I ask, I could say, compute the cosine of 3.4 pi divided by e. There it is. I want you to calculate the cosine of some number, and I'm going to. This will be in radians. So I'm saying compute this cosine. I mean, you can do this in your calculator, right? You enter that, and you press the cosine button, and you get a number. There will be some decimal number between -1 and 1. So you get some sort of a number, and it will look like this, plus or minus 0 point, and there'll be some number of decimal places depending on your calculator, or depending on how you go ahead and calculate it yourself. And 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So I mean, maybe a standard calculator would give you 8 decimal values there, or maybe 10 depending on your calculator. And how does your calculator do that? Well, I mean, one way would be that it's not looking it up. It's not, the values are not stored inside your calculator. So one way would be that your calculator would have the Taylor series for the cosine function, which let us just remind ourselves what that is. The cosine function is even, so that that looks like this: 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial. So we have a Taylor series approximation for the cosine function. So what your calculator can simply do is decide how many of these do you need to include so that you can get 8 decimal places of accuracy. Simply truncate after that many terms and give you the number. You have no way of really, in fact, knowing anything different. So it's no different for me to do that with this function here. And in fact, this function that we have produced here, that is the solution to the area equation, does not have a representation in terms of these elementary functions that we already know about. Okay, that concludes the second part of section 5.2 and 5.3 on series solutions near an ordinary point. Thank you.